right, well, welcome to this lesson here on polyatomic ions. We actually have two of them coming up here. So this is the first of two, but this is sort of the overview of how to deal with polyatomic ions. It turns out that these kinds of ions are really important in chemistry. We use them quite a bit, not just the single monatomic ions like we've been dealing with in the earlier lessons, but these little clusters of things. So you should have been given a list. Hopefully you've been practicing identifying these different polyatomics, because otherwise this is going to be really confusing as we go through this. So, hey, that's what you can hit pause and rewind for, right? So here this one. First thing, what's a polyatomic ion? The basic stuff is these are little clusters of atoms that all together are bonded together as a unit, and this unit now has a charge. As opposed to a single ion with a charge, which would be gaining or losing electrons. That's what we've dealt with before. Now we have these little clusters. These guys are covalently bonded together, so they form almost like little molecules, basically. But instead of being a true molecule with zero charge, these little molecule-like things have a charge to them. And in most cases, it's sort of a central atom with a variety of other little atoms stuck to it, like these ones that are on the screen here, that all have some sort of a central atom, and usually oxygen's kind of sticking to them. Pretty common. Again, these things are covalently bonded within, so they form a really stable little unit, and they never want to separate within that little unit. So once we have nitrate's always a nitrogen and three oxygens. We never split that apart. Those guys always stay glued together very solidly. But because they're an ion, then they can, as a group then, attach to other things like, say, sodium or magnesium and form some salts that way. So a little bit more complex than the ones that we have dealt with in the past. So a little bit more on the structure on these things. So first of all, most of the ones that you've got on your list are what we call oxyanions. So they're anions, meaning negative charges, and oxy, meaning that there's oxygens involved in them. And most of those oxyanions have this sort of format, where you've got a central atom that's usually a nonmetal, like sulfur or nitrogen or chlorine, and then you have a cluster of oxygens around the outside, either 3 or 4 oxygens usually, depending on which particular oxyanion it is. But it's always a repeatable sort of group. So if we have nitrate, you've got a nitrogen atom in the middle, you've got 3 oxygens kind of bonded to that nitrogen, and that whole group together has gained 1 electron, so now it becomes a -1 ion known as nitrate. Sulfate, like the ones on there, very similar. You've got sulfur in the middle, and in this case now there's 4 oxygens bonded to it. And in this particular case, with that structure, they would have 2 additional electrons to become a -2 anion. With all of these oxyanions, we start off with the basic idea of an ate and an ite form. The ATEs are usually what we would consider to be the most common or the representative form. And then the ITE form always has 1 less oxygen than the ATE form. There's no shortcut for figuring out which ones are which. You just have to memorize which ones have 4 oxygens as an 8 and which ones have 3 oxygens as an 8, like there's one example of each here. So that can be a little bit frustrating. It just takes practice. And then the other thing to kind of keep in mind, students, sometimes when they see this, they want to stick oxygen in the name somehow, like sulfoxyate or nitroxyate. I don't know where that comes from, but we never name the oxygen. The ending ATE or ITE sort of assumes that oxygens are already present in there. It's indicative of that element being present. Okay, briefly, I'm not going to talk a bunch about structure, but the students a lot of times ask, why are they different? Why is it sometimes 2, sometimes 3? And it really comes down to a question of bonding and stability. When these are forming these covalent bonds, these sharing arrangements on the inside, sometimes they're happy, I guess, with forming 3 different bonds. Sometimes they need 4 different bonds. Sometimes it's only 2. And the difference between them simply comes down to a rearrangement of how those electrons are shared. And that's why we have the ate and the ite form. The ate form, like I said, tends to be the representative form. The ite form tends to be 1 less oxygen and a slightly different rearrangement to them. Again, it feels kind of random. Please be aware that there are reasons for it. In the second semester, we'll start to draw this type of diagram, which are called Lewis dot diagrams, and kind of learn why they have that shape. But for right now, it's probably easier on you if you just go through the process of memorizing it. Sorry, but it really is easier at this point in time. So in terms of writing names and formulas, you just got to memorize them. It's just practice, practice, practice. Flashcards, Quizlet, whatever you got to do over and over and over and over and over again until it just becomes sort of reflexive to you. When you're writing names, if you've got a formula in front of you, well, there'll be some on the next screen. The process for writing the names out, the chemical names, is actually pretty straightforward. Number 1, you write the cation. If it's a transition metal, don't forget to include your Roman numerals. We do have one cation that's a polyatomic called ammonium, NH4, with a +1 charge, so watch out for that one, and it's got its own name. And then you write the anion, just like we've done before. Typically our anions in this case now are polyatomics, so you don't have to do any weird ending changes because the polyatomic name is the name that you use. So you don't have to change it to nitrateide or anything weird like that. Nitrate is the name of that. The only time you have to watch for the ending is if you're using a monatomic anion. You do have to do the IDE ending like we've done in the past. So let's take a look at some examples for this. On the screen I think we've got, what, six different examples of some compounds, formulas that are written that all contain at least a polyatomic ion. So your job right now would be to see if you can hit pause and see if you can sketch some of these out, give them a guess. Again, you name the cation, use a Roman numeral if necessary, or ammonium, and then you name the anion. I'm going to do a pause and then we'll come back and I'll go through them one by one. You ready? Okay, here we go. So, kind of from top to bottom. That top one up there, Li3PO4, that one's what we would call lithium phosphate. Lithium's an active metal, so we don't need any Roman numerals to it. And that 3 is there is because phosphate is a 3- charge and lithium's a 1+ charge. The next one down is nickel nitrate. So nickel is a transition metal, therefore we have to use a Roman numeral with this. And I kind of did that working backwards, knowing that nitrate's a 1- and there's 3 nitrates. That means the nickel has to be a 3+. So that's why it's nickel 3 nitrate is its true formal name. Next one down is calcium and acetate. Ca is calcium ion, it's a 2+. CH3COO is known as the acetate ion, and it's a 1-. So no Roman numerals are required in this particular one, calcium acetate. Coming up next, here's our weird cation. NH4 is known as ammonium. It's the only positive polyatomic that we have, so we've got to just kind of learn to look out for that one. And then the Cl means chloride, so this one's just ammonium chloride, no Roman numerals or anything else weird to there. Again, the ending on this one is chloride, IDE, and not AT, because it's chlorine as a monatomic ion, so all by itself. Okay, next one down, CuSO3 is known as copper 2 sulfite, ITE, so be careful with this one. SO3 is the sulfite form, SO4 is sulfate. I know it's copper 2 because both sulfate and sulfite have a 2- charge, and there's 1 copper to balance that out, so it has to be copper 2+ and cation. And then the bottom one, Fe2SO4, this one's a little bit tricky as well. There's our sulfate that I was just mentioning a second ago, SO4. The Fe2, this has to be iron 1 sulfate. So let's talk it out. Sulfate's a 2-, and again, that's a memorizing kind of thing. If it's a 2-, there has to be 2 irons to balance that out. Each iron has to have a +1 charge in order for the total of the cations to add up to 2+ to balance out that single sulfate, which acts as a 2-. That one was tricky. The last two were both a little bit on the trickier side. So if you had trouble with those, that's a pretty good place to have trouble. Okay, in terms of writing formulas, here's a couple practice problems. I'm going to run through one with you and then give you 2 to kind of practice with. So don't forget the rules that you've already learned about naming and writing formulas. That if you're talking about active metals, make sure that you're getting your charges from the periodic table. The anions, you should get those charges from the periodic table as well. If they're the polyatomics, you have to memorize those, so that can be kind of a pain in the butt, sorry. For transition metals, don't forget you need to use Roman numerals with those. And you're going to use your crossing down to figure out what your formulas are. And then the last thing is that when dealing with polyatomics is that you have to put parentheses around polyatomics if you ever want to use a subscript number with those. So let's take a look at an example. We're going to do magnesium hydroxide kind of together, I guess, and then I'll give you a chance to do the last 2 by yourself. So here's how I would attack magnesium hydroxide in writing the formula. First of all, I'd figure out what my 2 ions are. So there's magnesium ion is Mg2+. Hydroxide ion is one of my polyatomics, and it's got a 1- charge. So an oxygen and hydrogen bonded together covalently with a -1 charge. Second thing I'm going to do is do my crossing down. So my 1 goes down by the magnesium, and my 2 goes down by the hydroxide. But here's the trick, because it's hydroxide, I now need to use parentheses around the hydroxide to put that subscript out there. This is what it looks like when you're done. If you don't put the subscripts in there, it's going to be marked in, or not subscripts, you don't put the parentheses in there, it's going to be marked incorrect. It can't just be MgOH2. It has to be Mg with parentheses, OH, and then a little 2 on the outside to indicate that you have 2 hydroxides, not just 2 hydrogens. I know that's a little bit strange. You'll get used to that as you practice. So now's your turn to pause. You want to try to write a formula for tin 2 nitrite and ammonium acetate. So hit pause, and I'll come back and do these for you here in a second. Ready for spoilers? 3, 2, 1. All right, tin 2 nitrite. There you go. Tin is Sn with a 2+ charge. Nitrite is NO2. Remember, nitrate is NO3, so this is nitrite, NO2. NO2 has a 1- charge. So when I want to balance my charges down from the tin to the nitrite, I have to put parentheses around the nitrite and put another 2 out there. That means there's 1 tin atom and 2 nitrite sort of polyatomic stuck there. Total of 2 nitrogen atoms and 4 oxygen atoms in that particular compound. All right, the last one, ammonium acetate. Yes, it is all right to have 2 polyatomics together, as long as the one of them's ammonium anyway. So here's what it is. I'd write ammonium first, NH4, it's a 1+. Then I would write acetate second, it's CH3COO, and it's a 1-. Because they're both +1 and -1, I don't need to do any weird subscript numbers or parentheses. So it's just written out like that. You don't combine anything. Some students want to kind of combine the hydrogens together, and you don't do that. So it's ammonium, NH4, acetate, CH3COO. So there you go. Basic introduction to dealing with polyatomics. There's a lot more. This requires a lot of practice on your part. The only way to do it is to really practice, practice, practice. I've given some practice problems in class. You can look up tons of practice problems online. There's Quizlet stacks. There's all kinds of stuff that you can do. But the only way you can do this is really just to do it and do it on paper over and over and over again. Some basic hints. Make sure that you've got your flashcards memorized. You need to know the names, formulas, and charges for all of those polyatomics. There are some patterns to those polyatomics. Most of them end in ate or ite, and we talked a little bit about the numbers there. There are a couple of polyatomics that do end in IDE, like hydroxide, cyanide, and peroxide. So you just have to kind of watch out for those. That needs to be like that sounds like one of those polyatomics. So again, flashcards. You need to memorize your charges. I've had you guys use colors, so if you have trouble remembering what's the charge of sulfate or nitrate, see if you can do that color memory, like, oh, it's green, so it's got to be a -1, or oh, it's purple, so it's a -2, and go through that process to help you remember what the charges of them are. But again, flashcards, flashcards, flashcards. There's a few of our 8s that have 4 oxygen and a few of them that have 3 oxygens. So our 4 8s, sounds kind of weird to say that, our 8s that have 4 oxygens are sulfate, phosphate, chromate, and permanganate. All of those are O4. So SO4, PO4, CrO4, and MnO4. They all have different charges, so I'm not saying that part. And our 3 8s are nitrate, chlorate, carbonate, and then bromate and iodate, which I don't believe I made you memorize in this particular chapter, but those guys are in there as well. So the 3 big ones are nitrate, carbonate, and chlorate that are the O3s, the 3 8s. Keep in mind that when you're writing formulas, you never, ever, ever change the subscripts to kind of try to make it work. You would never change it from an NO3 to an NO2 because it doesn't really change the charge. That would indicate something else. And then the last thing is, as you're balancing these, you can almost pretend like that polyatomic is like an X. Like it's one thing. So if you want to change something, you have to put parentheses around it in order to get a little subscript on the outside. You're not allowed to just tack something on. But treat it like one whole object, like I said, like an X or something like that if you want to, or make a big square and fill it in later. But it's a single unit, and they act like a single unit when they kind of add and subtract with one another. So there you go. I hope this helped a little bit. Like I said, I know it's a little bit painful. Just do your best. Practice, practice, practice. Lots more flashcards. Make another lap through even right now as we're talking. Okay? All right, and I will see you in class. Good luck.